Today we're looking at nitrogen reduction and the Haber Bosch process. Now, the Haber Bosch process has been around for about 100 years. It's used for fertilizer production, taking nitrogen from the atmosphere, combining it with hydrogen gas, and producing ammonia. And ammonia is used globally for agriculture, increasing crop yields by significant amounts. So this is a very important reaction. However, it's extremely energy intensive. Part of the reason you could imagine is that we've got to take that strong nitrogen-nitrogen triple bond and break it if we're going to convert the nitrogen to ammonia. And so it requires very high pressures and very high temperatures. And that in itself is a bit of a problem thermodynamically because free energy is equal to enthalpy change minus T delta S. So as temperature gets larger, this term becomes more important. And this reaction takes 4 molecules and converts them to 2. And so entropically, this reaction is driven this way. So it would be great if we could come up with a process that doesn't require such high temperatures. And that might make this nitrogen conversion into ammonia even more efficient. Now, I didn't mention that this reaction requires heterogeneous catalysis. So it's done over some reduced iron or ruthenium ores. And all of these conditions, the high pressure and temperature and this heterogeneous catalysis, makes the Haber Bosch process a little bit difficult to study directly. And so a lot of what people know about it when they're trying to learn how this works comes from modeling studies, looking at different compounds that might carry out part of this reaction, but not the whole thing, to try to understand how this really could work. Also computational chemistry, building intermediates in a computer, calculating their energies and so on to try to find out what seems like a viable process to get from nitrogen to ammonia. And if you think about it, we might be able to come up with some ideas of how this reduction of nitrogen to ammonia could work, either in the Haber Bosch process or in some process that we haven't come up yet. And if you remember some organometallic reactions, you might think maybe we can take that hydrogen, oxidatively add it to the iron to get hydrides. And then you could do some insertion reactions onto the nitrogen. And then a reductive elimination to get the second hydrogen on to form this diazine intermediate, and so on. Now, the studies, a lot of the studies that have looked at Haber Bosch don't point towards that mechanism. And the reason is because of these iron nitrides. There's been a fair amount of evidence that nitrides like this are forming on the surface of heterogeneous catalysts that are that can carry out these kinds of transformations. And so the nitrogen-nitrogen bond may be splitting before the hydrogen comes along. And so that would be done through presumably some sort of oxidative addition. And it would require cooperative activity between more than one iron atom. And remember, this is a heterogeneous catalysis. This is all taking place on this iron surface. There are lots of iron atoms on this surface. And so some sort of cooperative activity is certainly possible. So here, each of these irons is donating 1 electron into the pi bond to break it. And we've oxidatively added the nitrogen, breaking one of those pi bonds. Now we'll break a second one and finally break the sigma bond and so on. The hydrogen could still come in through oxidative addition, but then it would go onto the nitrogen simply by reductive elimination. So these are some of the thoughts about how the Haber Bosch process works, and it's an area of active research. People are very much interested in finding new ways to carry out this reaction so that it can be done more efficiently.